Hello students, let's continue our chapter thermodynamics. Here you can see the system and surrounding is being given, and we know that energy is mainly exchanged as heat and work, okay, between the system and the surrounding. So now as heat energy, we can see, suppose a system is taken as hotter. Now for example, a beaker filled with water is kept with a lid on the top, and it is kept for a while, and what we can see is that it acquires the same temperature as that of the surrounding after a while. Okay. So we can say that the system transfer its heat to the surrounding. Okay. So we can write Q as Q is given as for heat, Q is given. So Q is equal to minus, that is negative. So it gives its heat energy to the surrounding. Okay. Now here we can say, we can take an example of cold drinks. Okay. Now cold drinks is kept for a while. So what we see that it also acquires the same temperature as that of the surrounding. So now here Q is positive. Okay. Now it so here it absorbs the heat from the surrounding to the system, from the surrounding. Okay. Now here it transfers its heat to the surrounding. So as you know that as I told now that it is as work energy, also we can say energy as work energy. Okay. So work can be classified into two types. First is electrical work, okay, electrical work, and second is mechanical work. So in electrical work, as you know that by passing electric current, the energy is transferred on passing electric current. In this you can see, for example, electrolysis of water, okay, the ions moves. Whereas in mechanical work we have PV, that is pressure and volume work. So it is pressure and volume work means it is mainly in gas, it is carried out as the system and gas. Okay. Now as you know, it is hardly you can see in solid and liquid, that there is no change in there is a slight change in volume and pressure. Okay. Now this is a cylinder. Okay. Now this cylinder is filled with gas. Okay. Now here is a frictionless piston, that is weightless piston. So it can move its own. So work done. So I can write work done on expansion. Work done on expansion. So this is earlier, now this is V initial, okay, and this is allowed to expand. This is allowed to expand at a distance. This is V final, okay. So at a distance L. So provided P external is less than P internal, then only this will move up. Okay. So this is the area of cross section. Okay. Now here expansion of the gas takes place, whereas here now this is V initial. So in this you can see that V final is greater than V initial, whereas here now this is V initial and this is V final. Okay. Now this is work done on compression. Okay. Now here this has been compressed. So, V initial is here and V final is here. So, it has been compressed to this level. So, this is also a distance of L. So, we know work done is equal to force into distance. Okay. Now, this force can be written as pressure is equal to force by area. So, force is equal to pressure into area. Okay. So, I will substitute this. So, work done is equal to pressure into A into distance. Distance is this. So, it is L. So, this is nothing but it is the change in volume. So, I can write del V as A, area of cross section, into that is the length. Okay. The change in volume takes place. Okay. Now, here I can write as P external into del V. This negative sign is added to obtain the conventional sign for work done. So, work done is equal to minus P external into del V. So, del V is nothing but it is V final. So, I can write minus P external as V final minus V initial. Okay. Now, we will see what will be the sign of this. Okay. Now, here work done on expansion. So, work done is equal to, so I can write P minus P external into V final minus V initial. Okay. Now, here V final is greater. So, W is what, that is negative. Okay. So, here the systems does the work, that is work expansion. So, work expansion is negative. Okay. Now, here for the case of compression, I can write for compression, work compression, here W is positive. So, work done on the system, this is by the system and this is on the system. So, we can write as positive. So, why positive? So, here I can write, so W is equal to minus P external, okay, into V final minus V initial. For the case of compression, so here V final is less than V initial. So, V final is less than V initial. So, what we will get, that is minus P external, okay, is into minus of V final minus V initial. So, this minus and minus into, so we will get what, W minus minus into, so we will get positive, that is W is positive for compression. So, in this way we got this, that is W compression is equal to positive. Okay, students. Now, we will see that is what is work reversible. So, students, for case of compression, P external can be written as P internal plus or minus that is dP, that is small change in pressure. So, this is for a reversible process. So, reversible process in which compression and so this is the reverse for reversible process, this is compression and this compression and expansion, both plus and minus takes place. So, work reversible can be written as, that is, P into delta V minus P external into dV. Okay. So, in place of P, V is equal to, in place of P external I can write PV is equal to nRT. So, P is equal to nRT by V. So, I will substitute this in this. So, we will get P reversible is equal to what? P reversible is equal to, I will substitute this. So, in that place we will get what? P reversible is equal to, yes, N. So, substituting this we will get what? P N R T V1, V initial, V final. Okay. So, which can be written as, that is dV by V. Okay. So, here what will be this? So, reversible is nRT ln V2 by V1. So, this natural logarithm is changed to the logarithm at base 10, that is R reversible is equal to minus of, here the minus will come, here the minus will be there. Okay. Now, here minus 2.303 nRT log of that is V2 by V1. So, this is the expression for V reversible. Okay. Now, in case of this we can change to pressure. So, we know V is inversely proportional to pressure at constant temperature. So, work reversible can be written as minus 2.303 nRT. Okay, nRT. So, log of P1 by P2. Okay, as this is inversely proportional. So, we can change this sign as V reversible is equal to 2.303 nRT log of P1 P2 by P1. So, this is for isothermal work reversible expansion. Okay. Now, so this is the thing. So, students, now we will see a numerical based on this. So, students, let us see a question. A 5 liter cylinder contained 10 mole of oxygen at 27 degrees centigrade. Due to sudden leakage through the hole, all the gas escaped into the atmosphere and the cylinder got empty. If the atmospheric pressure is 1 atm, calculate the work done by the gas. So, here 5 liters. So, first we will see the calculation of final volume, calculation of change in volume. Okay. So, V initial is 5 liter given. Okay. So, V final we have to find. Now, 10 moles of oxygen. So, number of moles 10 moles and 27 degree centigrade, the temperature is given as 27 degree centigrade. So, I will convert it into Kelvin. Okay. Now, atmospheric pressure, that is pressure is 1 atm. 1 atm. Okay. Now we know that is PV is equal to nRT. So where PV for an ideal gas, PV is equal to nRT. So we have to find this volume. So V is equal to nRT by P. So V is equal to, that is final volume, that is N is 10 into R is 0.082821 liter atm K inverse mole inverse. This is the unit, into temperature is 300 Kelvin divided by pressure is, here pressure is 180. So when we calculate, the volume will come to be 246.3 that is liter. Okay. So this is the final volume. So now we will see the change in volume. Delta V is equal to that is V final minus V initial. So V final is 246.3 minus 5 liter. Okay. So it will be 241.3 liter. So now we will see the work done by this gas. Which gas? Oxygen gas. Okay. So work done by the system, or you can say that the gas is equal to, W is equal to minus P into del V. So minus of that is, we have 1 atm, pressure as 1 atm into 241.3. This is in atm, 1 atm, and this is in liter. So 1 liter atm is equal to 101.3 joule. So I will convert it into joule. So when I convert to, this is minus 241.3 into 10 to the power 101.3 joule. So it comes to be 24444 joule. So work done in joule. So in kilojoule it will be 24.444 joule. Okay students. So this is the required work done by the system, the work done by the oxygen gas. So now we will see a video for enthalpy and rest of the topics.
We have learnt that if a process is carried out at constant volume, then the heat content is the same as the internal energy as no work is done. But most of the chemical reactions are carried out at constant pressure and not at constant volume. When a reaction is performed under constant pressure, then it may involve change in the volume. The energy change occurred during such reactions may not only involve change in internal energy but also do some work. To understand this, assume a chemical reaction occurring at a constant pressure. Let us assume that the reaction is exothermic and also involves gaseous substances. When the reaction proceeds at constant pressure, two possibilities arise. One possibility is that if the reaction is carried out with increase in volume, then the system has to expand against atmospheric pressure and energy is required to perform this act. As some of the energy has to be utilized for this purpose, the heat evolved in this case would be a little less than the heat evolved at constant volume conditions. The other possibility is that if the reaction is carried out with decrease in volume at constant pressure, then the work is done on the system and heat evolved would be greater than the heat evolved at constant volume. Thus, it can be concluded that heat changes occurring at constant pressure and temperature are not only due to change in internal energy but also due to expansion or contraction against the atmospheric pressure. Hence, the scientists felt the need to study the heat changes at constant pressure and temperature. In order to study the heat changes in a chemical reaction at constant temperature and constant pressure, a new thermodynamic function called enthalpy was introduced. The total heat content of a system at constant pressure is equal to the sum of the internal energy and PV. This is called the enthalpy of a system, which is represented by H. Note that enthalpy is also called as heat content. Enthalpy, which depends on the three state functions, internal energy, pressure, and volume, is also a state function. Every substance has a definite value of enthalpy. Like internal energy, enthalpy of a substance cannot be measured. However, it is possible to measure the change in enthalpy. The change in enthalpy is equal to the difference between enthalpy of products and enthalpy of reactants. The change in enthalpy may be expressed as delta H is equal to enthalpy of products, HP, minus enthalpy of reactants, HR. The significance of delta H also follows from the first law of thermodynamics, as delta U is equal to QP minus P delta V. Here, QP represents the heat absorbed by the system and minus P delta V represents the work done by the system. Let U1, U2, V1 and V2 represent the initial and final internal energies and volumes respectively. The above equation can be written as U2 minus U1 equal to QP minus P into V2 minus V1. On rearranging this, we get QP equal to U2 plus PV2 minus U1 plus PV1. But we've already learned that U plus PV equal to enthalpy H. Hence, the equation can be written as QP equal to H2 minus H1 is equal to delta H. Therefore, delta H is equal to QP. For finite changes at constant pressure, we can write the equation as delta H is equal to delta U plus delta PV. Since P is constant, we can write as delta H is equal to delta U plus P delta V. Remember that delta H is equal to QP, the heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions and positive for endothermic reactions. Let's now look at the relation between delta H and delta U. When we deal with solids and liquids, the difference between the change in internal energy, delta U, and enthalpy, delta H, is not significant. This is because solids and liquids do not show significant change in the volume when heated. Thus, if change in volume, delta V, is insignificant, it implies that change in enthalpy, delta H, equals change in internal energy, delta U. The difference between the change in internal energy and enthalpy becomes significant when gases are involved in the reaction. Let's consider a chemical reaction occurring at constant temperature, T, and constant pressure, P. Now, let's say that the volume of the reactants is VA and the number of moles in the reactants is Na. Similarly, the volume of the products is VB and the number of moles in the product is NB. We know that according to the ideal gas equation, PV equals nRT. Thus, for the reactants, PVA equals NART, and for the products, PVB equals NBRT. Thus, PVB minus PVA equals NBRT minus NART, or PVB minus VA is equal to NBRT minus NART, or PVB minus VA equal to NB minus NART. That is, pressure P multiplied by change in volume, delta V equals change in number of moles of gas, delta N GRT. Note that delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. We learnt that change in enthalpy delta H equals change in internal energy delta U plus product of pressure P and change in volume delta V. On substituting the values, we get change in enthalpy delta H equals change in internal energy delta U plus change in number of moles of gas delta N GRT. This relation helps us in calculating the change in enthalpy from change in internal energy and vice versa. Now let's learn about heat capacity. The capacity to absorb heat energy and store it is known as the heat capacity of a system. The heat absorbed by the system appears as rise in temperature. The increase in temperature is proportional to the heat transferred, which can be written as Q equals coefficient multiplied by change in temperature delta T. Note that the value of the coefficient depends on the size, composition, and nature of the system. The equation can also be written as Q equals C multiplied by delta T, where C is called the heat capacity of the system. If Q calories is the heat absorbed by the system and the temperature rises from T1 to T2, the heat capacity C is given by the expression C equal to Q by T2 minus T1. Thus, heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree at a specified temperature. The specific heat capacity is the quantity of heat required to raise the temperature of unit of mass of a substance by 1 degree Celsius or by 1 Kelvin. Thus, the expression for Q in terms of specific heat capacity becomes Q equals specific heat capacity C multiplied by the mass m multiplied by change in temperature delta T. The molar heat capacity of a substance is defined as the quantity of heat needed to raise the temperature of 1 mole of substance through 1 degree Celsius or 1 Kelvin. The SI unit of molar heat capacity is Joule per degree Kelvin per mole. The molar heat capacity Cm equals heat capacity C divided by N, where N is the amount of the substance. Heat is not a state function, neither is heat capacity. Hence, it is necessary to specify the process by which the temperature is raised by 1 degree.